Hello. A little long intro there, sorry. Good evening for me, good whatever it is as you're watching this. This is the VOD that will be officially posted for 8 a.m. on Tuesday morning, May 25th. This is the VOD version of the lesson that has been improved by the feedback of your peers who were able to make a live lesson. Our goal today, a little bit of admin stuff, and then we're going to talk about Taylor polynomials. We've been doing Taylor series, remember? We're going to talk about some complications from using them. We're going to introduce the one big theorem of this section and do one little proof bit. Not much. The rest of 9-7 we're going to finish tomorrow. So an optional live lesson on Tuesday and post it as a VOD for Wednesday. And that's going to be this week. We're going to take it a little easy. This is the last regular sort of material of the course. So there's no reason to rush that. You guys have had a busy couple weeks with APs and managing your coursework on top of it. So we'll take this a little lighter, and that's totally fine. A little bit of administrative stuff. Nope, I'm so sorry. The administrative stuff I had to do with differential equations this morning. You guys didn't really have any. We're good to go. So that is the plan. That's what's going on. With no further ado. The good news here is you already know what a Taylor polynomial is. We've been doing this. No big deal. Contrast with that we know a Taylor series of f at c is a sum of the nth derivative at c divided by n factorial multiplied by x minus c to the n, right? Something we've been studying, something we have been working with, no problem. A Taylor polynomial of f at c of degree n would be a sum of the kth derivative of c. I already used n for something, right? Can't use it again as an index. K factorial x minus c to the k. And you should be saying to yourself, wait a minute, there's something important missing here. This is the same thing. It's just a k instead of an n. What gives? And you should recognize how to fix it. What we're missing, of course, are the added bits of information about the summations, right? The index for our summations. Here we're saying n goes from 0 all the way to infinity. We're doing the infinite sum for all the terms. Whereas only up to degree n, we're saying start at the 0th power, yes, but stop at the nth power. Only go up to n. And indeed, what you may notice, what I hope you notice, is that a Taylor polynomial is just a partial sum of the Taylor series. You want to be careful about describing which partial sum it is. If you say the nth partial sum, well, since we start at 0, does that mean we stop at n minus 1, so we have n terms total? What if some of the terms are 0? Do you mean n non-zero terms? But certainly it's the partial sum that goes up to a degree of n, right? So that the highest degree is not bigger than n. So a Taylor polynomial is just a partial sum of the Taylor series. No problem. And we also discussed what we'd use this sort of thing for, right? We did, in fact, some integrals, which would be difficult or impossible to compute otherwise. We talked about how you can approximate, as well as being able to approximate in more general circumstances, such as example number 1. What if I'd like to approximate sine of 2 degrees, and I'd like to claim that this is approximately equal to the second Taylor polynomial, the Taylor polynomial of degree 2, evaluating at 2 degrees. Well, we know a Taylor series for sine of x already. We know x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. So if I want the second degree Taylor polynomial, I'm just saying cut it off at x to the second power. So we actually have 0x to the zeros plus 1x to the first plus 0x squareds, which is to say just x. So the second degree Taylor polynomial is actually equal to the first degree Taylor polynomial in this case. Something worth noticing. It's okay though. And therefore I claim that sine of 2 degrees is approximately equal to 2 degrees. And you should be objecting here as well and saying, wait, Schwartz, this is not good for calculus. Something is problematic. We have an issue. And indeed, you're correct. We're using degrees. We should not be using degrees. That's not a good plan. We could say that sine of 2 degrees is approximately pi over 90 radians, which is to say the value pi over 90. And in increasingly rough approximations, I could say that's very roughly 3 over 90, which is 1/3, which is very roughly 0.03, right? It's clearly not 0.03, right? We know that. But as a very, very broad approximation, yeah, this is plausible, right? This is just a sanity check, just making sure nothing's completely crazy right now. Reasonable sanity check. So there's example 1. Using Taylor series, using Taylor polynomials to approximate the value of sine of 2 degrees. Great. Let's do a second example. Example number 2. What about doing sine of 61 degrees? This should be approximately equal to the second degree Taylor polynomial evaluated at 61 degrees, which we just did. So this is x evaluated at 61 degrees, which would be 61 pi divided by 180. That would be converting the degrees to radians to an actual value, which is in turn approximately 60 times 3 over 180, which is 1. Excuse me, one sec. So we claim by using the second degree Taylor polynomial that sine of 61 degrees is approximately 1. And again, this was just getting rougher as we went, right? I assumed that not only am I using approximation in the first place, but then that pi is 3, that 60 is 61. That's not particularly reasonable. Something went wrong here, right? This wasn't a good approximation anymore. I mean, we're not that far off, right? In terms of order of magnitude, yeah, okay, fine. But this isn't that great, right? We should be able to do better than this. Just looking at sine of 61 degrees, you know you can do better than this. Because we know what sine of 60 degrees is. Huh. Well, there's one good way to make our approximation better. How about instead of using the second degree Taylor polynomial, let's use a higher degree polynomial. Let's use more terms, right? That should certainly help. That should make things closer to the real value. So let's use P3. Let's use the third degree Taylor polynomial. So we get x minus x cubed over 3 factorial evaluated at 61 degrees. Which of course gives us, converting to radians, 61 pi over 180 minus 1/6 times 61 pi over 180 cubed. So we're going to get rougher here. This is very roughly 60 times 3 over 180, which is about 1. This is the sanity check part, right? We're getting a rougher and rougher approximation here. And this is minus 1/6, then that would be approximately 1 cubed, right? About 60 times 3 over 180. Which would give us 5/6, which is 0.83 repeating, and that's actually not that far off from root 3 over 2, which is of course about 0.86. This actually wasn't so bad. Just by using one additional term, this is a pretty good approximation, right? Not bad at all. We can work with this. Notice also that 61 pi over 180 is a little more than 1. So in fact, our real value would be a little more than 0.83 repeating, and it should be. Not bad. Really not so bad at all. So how do we make that better? We use more terms, right? Which makes sense. It seems reasonable. If we use more terms, we'd get a better approximation. One more example. Example 3. That sine of 722 degrees should be approximately the second-degree Taylor polynomial acting on 722 degrees, which, as we know, is x evaluated at 722 degrees, which would be 722 pi divided by 180, which is approximately 720 times 3 divided by 180, which is 12? Wait a minute. That's not good at all, guys. We got a problem, right? That's an awful approximation. That's a full order of magnitude off, in addition to the fact that it's more than 1. Sine of 720 degrees, sine of anything, can't be more than 1. This is ridiculous. Option 1. Yeah, we can include more terms. It's an option. But really the question is, could we do something that would make more sense here? One of your peers, in discussing why this is so problematic, came up with an excellent suggestion, which is that we need to be thinking about the radius of convergence. Maybe 722 degrees isn't even in the radius of convergence, in which case, of course, this isn't a good approximation. Part of your assignment, due this upcoming Wednesday, is to work with some Taylor series to find some radii of convergence, and you may or may not do it exactly for sine, and that's okay. If you have, my hope is that you have some recollection of that radius of convergence for sine, of the interval for sine. And if you don't, that's okay. You can go do it yourself if you'd like, or take for granted. The Taylor series of sine of x converges for all real numbers. So checking the interval of convergence, excellent idea. But 722 degrees is inside the interval of convergence. Thing 2 to think about. For just 2 degrees, the second-degree Taylor polynomial was pretty great. For 61 degrees, it wasn't that far off, right? It was 17% off or so. It wasn't awful. Not as good, though. And now out as far away as 722 degrees, it's terrible. There is a follow-up idea to interval of convergence, to where you converge. Not just where, but how quickly. At what rate do you converge? And that actually becomes a very important issue later on in some other courses, in some other contexts. It relates to, but isn't limited to, the idea of uniform convergence, which is when the rate of convergence is independent of where you're checking. I would argue here that the rate of convergence for this Taylor series centered at 0 of sine of x is faster near the center, near 0. For 2 degrees, it was very quick. We only needed one term to get a pretty good approximation. At 61 degrees, we needed 2 non-zero terms. We needed n equals 3. Still not that bad, but we needed more, right? We needed more work to converge. Sorry, to get close to where we converge, to get a small error. And once we get as far away from the center as 722, we are converging rather slowly, let's say. This single bit of work isn't enough to fully justify that, but if we did p sub 3, if we added on another term here, it'd still be pretty far off. So not only could we improve our approximation by adding terms, maybe there's something to do that we can do with our series to affect the rate at which we converge given the input in which we're interested. For 2 degrees, the series we made converged quickly enough that our approximation was good. For 61 degrees, it still wasn't awful. Could have been better, though. And for 722 degrees, this is not going to converge quickly enough for our approximation to be an effective one, right? A strong one. Well, what else could we do? What if instead of centering at 0, what if we center at, say, 720 degrees? So that our approximation is still do derivatives, plug in 720 degrees, and in the context of trigonometry, that's the same as our values of plugging in 0 anyway. So in fact, the coefficients of our sequence don't change. We get 0 multiplied by x minus 720 degrees to the 0. We get 1 multiplied by x minus 720 degrees to the 1. we get 0 times x minus 720 degrees squared, technically 0 over 2 factorial, right? But that's still 0. And we get minus 1 over 3 factorial x minus 720 degrees cubed. Well, notice when we were using our original Taylor series, when we were using the Taylor series centered at 0, plugging in 720 degrees for x and cubing it gets pretty big. And raising it to the 5 also gets big, right? We're plugging in a number greater than 1. Raising it to higher powers is getting larger. Eventually, the factorial will dominate, right? Factorial grows faster than a power series, then cubing, raising to the 5, etc. But it'll take time to get there, right? For smaller values. If x is large enough, small values of n means the numerator might be dominating right now. The denominator only gets a factor of 20. The numerator gets a factor of x squared. So if x is large, right now, the numerator is growing faster. The entire series converges slower. But if we recenter, if I plug in 722 degrees now, I'm doing 2 degrees to the first, to the second, to the third. 2 degrees is much less than the number 1. So raising it to higher powers gets smaller as we go. Not only do my denominators get, well, not only do my terms get smaller because the denominator is getting bigger, but my numerator term, my x minus c to a power term, is also getting small here. So by recentering, we can cause our numerators to contribute to the speed at which we converge. The goal is c such that x minus c is small. That way we don't have to wait and rely on factorial outgrowing the exponent. We can use both together to get small very rapidly. Let's revisit example 2. Instead of adding the n equals 3 term, the third power term, using a polynomial of degree 3, let's revisit example 2. What if we centered a series for sine of 61 degrees at 60 degrees? We get that sine of x is, and here's where we have to be careful. As I take derivatives, starting with the 0th derivative, now I'm plugging in 60, not 0 or 720 degrees. And I actually messed this up this morning. I wasn't thinking. The 0th derivative of sine of x is sine of x, so I need sine of 60 degrees divided by 0 factorial, x minus 60 degrees to the 0. To which we add the first derivative, which is cosine of 60 degrees divided by 1 factorial, x minus 60 degrees to the 1. To which we add the second derivative, negative sine evaluated at the center over 2 factorial, x minus 60 degrees squared. And to which we add the third derivative, negative cosine of 60 degrees divided by 3 factorial, x minus 60 degrees cubed, and etc. Sorry, again, etc. or and so on. I need to remember that. So notice here, not only are our denominators rapidly increasing in size, but the terms by which I'm going to multiply are shrinking because 61 degrees minus 60 degrees is small. The closer to your center, I can't say that, right? Because some series don't. For many series, the closer you are to the center, the more rapidly you converge. The quicker that the error, the remainder, gets small. So let's do this, right? Sine of 61 degrees is therefore approximately sine of 60. That's a root 3 over 2 divided by 1 times 1 degree to the 0. Plus cosine of 60 degrees is a half over 1 times 1 degree to the 1, and so on, which is approximately root 3 over 2 times 1 plus a half times, well, 1 degree is pi over 180. So we just get root 3 over 2 plus pi over 360. Yeah, that's pretty good, right? I'm definitely close to root 3 over 2. That was the value at 60. How close? Well, I'm off by approximately 1 over 120. Yeah, not bad. That'll do. That's pretty solid. So how do we make a better approximation? You can use more terms, or you can move the center. And the key to moving the center is there are two things to worry about, right? We'd like the center to be close to where we're approximating, but we also need something else, right? Why didn't I just center this at 61 degrees? That would be even better than at 60 degrees, right? The closer, the better. We don't know the value of sine of 61 degrees, right? We'd have to plug in the center here. That's what we're trying to get. Nor the derivatives there at 61 degrees. You have to balance choosing a center close to your value and choosing a center such that the computations are easy, that evaluating, getting values for your derivative terms is straightforward, is reasonably computable. So you get as good a center as you can, and then if you just have to add more terms, then you add more terms, right? First step, get a decent center. Second step, add terms if necessary. We are up to our theorem. The theorem of the section. This is the theorem of the Legrange error bound. And as pointed out by a peer, this is strongly reminiscent of something else we've studied, which I hope you notice as we see it. But this is the Legrange error bound. I'm actually not sure if Legrange did this or if it was just named for Legrange. In math, it can kind of go either way, so hard to say. F being differentiable through the n plus first order, which is to say I can do at least n plus 1 derivatives, on an open interval I containing the center C. Then for all x in the interval I, there exists a z that lies between x and c. So if x is less than c, it would be x to c, or alternatively c to x, right? It just depends on where x lies compared to c. Really what we're saying is there's a z between the x and the c, such that f of x is exactly equal to the nth degree Taylor polynomial plus a remainder term, where I can explicitly write that the remainder term is equal to the n plus first derivative at that unknown point z over n plus 1 factorial times x minus c to the m plus 1. I don't know what point lying between the spot I'm plugging in and my center is the one that makes this work. But I claim that there is one. Corollary. Bear with me for a sec. The corollary might actually make a little more sense. This is why we care. This is what we're doing with this. That the absolute value of my remainder is the error of the approximation if I just use my Taylor polynomial, right? If I plug in a value and I approximate using Taylor polynomial, well, the difference between the real value and my approximation is r. So that's the remainder. I claim that we can bound our error. I'm going to take the x minus c to the n plus 1 term and use an absolute value, right? Because error should be positive. I'm going to divide by that same n plus 1 factorial, no problem. And I'm going to say I'm going to multiply by some k, such that k is the maximal value of the absolute value of the, let's use an x here, of the derivative. I can't use x. I gotta use z. All right, I didn't want to use z because it's actually a little confusing, but I'm using z, sorry. That's a z, I promise. That k is the maximum of the absolute value of the n plus first derivative. It's this piece, right? I'm just saying the maximum it can be for all z lying between x and c. So I might need to think about the interval c to x, right? I'm doing the same thing that we had just been talking about. I don't know what z is, though. So I'm saying if you think about all the possible things z might be and you find the max, Well, if the remainder is exactly equal to a specific one of them over n plus 1 factorial, x minus c to n plus 1, then certainly it can't be more than the biggest possible value among these z options times the same term otherwise. And this looks very similar to when we approximated error for Riemann sums. And it's the same general concept, right? The more terms we have, the smaller the error bound. The closer x and c are together, especially if x minus c is less than 1, the better off our error bound is going to be. And the more wild the next derivative can be, right? The worse off my max can be, the worse off my error is. Same idea. Of note, we often don't compute k exactly. Think about what you need to do to get a max of a function. We need to do optimization, right? We need to find its derivative. And you can do that. You can find the max of f of n plus 1 in this interval. That said, meh. If, for example, your derivatives are sines and cosines, we know it's less than 1, right? And even if you could do better, even if you could say, no, the max in this particular interval is a half, the difference between plugging in a 1 and a 1/2 for k just isn't that big a deal, right? It's just not that big a deal. So it's common, I'd like to note, common to approximate k with something bigger. So instead of using the exact value of the maximum of the derivative between x and c, we generally say, look, I know that the value here in my interval can't be bigger than 10. So I'm just going to use 10. That's good enough, not a problem. Right? Same idea that we did before with Riemann sums, with error for Riemann bounds. Last thing for the day. As mentioned, shorter, right? Taking it a bit easy today, and then we're going to pick it up with some proof, some more heavy-duty stuff tomorrow. Last part for today. So again, we're going to be talking about our setup here, talking about the same stuff we've been working with. And let's consider specifically the n equals 0 case. What if I use a 0th degree polynomial to approximate my f? What can we say about the remainder? We're claiming that f of x can be written as a 0th degree Taylor polynomial plus the remainder for n equals 0, where there exists a z such that the remainder is exactly equal to the n plus first derivative. So n is 0, that's a first derivative at z, divided by n plus 1 factorial is just 1 factorial, x minus the center to the 1. Let's play with this a little bit. So first of all, what is a 0th degree Taylor polynomial? Well, it's the 0th derivative at the center divided by 0 factorial times x minus the center to the 0. Well, the 0th derivative is just the function. 0 factorial is 1. Anything to the 0 is 0. We just get f of c here. Okay. So let's plug it in. We're claiming that f of x is equal to f of c plus the remainder, which I know 1 factorial goes away. All right, that's fine. F prime of z times x minus c. Where have we seen before a theorem that claimed there is a z that somehow relates the derivative at z, the unknown place z, with f of x and f of c and x minus c? And we've seen this before. If I solve this for f prime of z, I'd subtract, I divide, I get f of x minus f of c divided by x minus c. The Legrange error-bound theorem states there exists a z between x and c such that this is true. Well, that, my friends, is just the mean value theorem. The n equals 0 case of Legrange error bound is the mean value theorem, which gives you a taste of just how broad and interesting this might get when we allow for cases that aren't just n equals 0. Trying to have a good, strong conclusion kind of gets messed up if you stumble over the terms, doesn't it? That's a shame. All right. So what did we do today? Talked about Taylor polynomials, talked about complications of them, talked about that one big theorem, Legrange error bound, and we did one little bit of proof. We looked at the n equals 0 case and recognized in that case, this is just the mean value theorem. Interesting. Formally, Taylor series versus Taylor polynomial, talked about how it's really a partial sum of the Taylor series. We did an example using sine of 2 degrees. And for the record, I chose 2 so that when I did one more, I'd get 3. But p sub 2 is equal to p sub 1 here, right? The second degree and first degree polynomials are equal in this particular case. For sine of x centered at 0, they're equal. We did a sanity check. We did a second example, and we got not a great approximation. Not awful, but not great. So we upped it. We used a third degree polynomial instead, and that was pretty close. Not bad at all. Even with a rough approximation, not bad. We did a third example, and this one was not good. And we talked about how recentering is sometimes a better strategy, a more powerful plan, than just using more terms. Especially if you can recenter so that x minus the center is less than 1. That relates to rate of convergence, in addition to the fact that something converges or not. We went back to example 2, and we recentered at 60. So this time, the first degree polynomial and the second degree polynomial would be different. We, in fact, used the first degree polynomial, not even the second degree polynomial here. And it was already very good. In fact, just the 0th degree polynomial wouldn't have been that bad in this case because we can be so close to 60 degrees. Right? There is a good center very close. Had we been doing, say, sine of 78 degrees, we would have needed to use either 60 or 90, and we would have been farther off. We would have needed more terms. Probably the first term would be enough, but it wouldn't have made sense to stop at only the 0th term. In this case, it would have, honestly. Not so bad. We introduced the Legrange error bound. Kind of a weird theorem, but a claim that an existence theorem, there is a z meeting a certain condition about the remainder. That the remainder term looks like the terms of your Taylor series, but there's a specific value somewhere between x and c, where if you plug it in place of c in your term here, your derivative term, you get exactly the remainder. A corollary thereof is that we can bound the remainder, and the remainder is just the error of your Taylor polynomial. And we talked about that in the n equals 0 case, the Legrange error bound theorem, it's usually not called that. It's just called Legrange error bound for the record. But Legrange error bound is the mean value theorem. How cool is that? Hello, analysis 1. We have found, Kirk and I, that the video that we're using for 9.7 from last spring is good, with one exception, that it's missing a couple examples that we ought to do. We didn't have those in the video. Those had only been live. So I'm going to add a couple examples, and Kirk is going to splice this in. So this intro that I'm giving is probably irrelevant, but just in case he includes it, I figured why not. Example number one. We're going to bound the error if we were using a Maclaurin series, of cosine of x with n equals 2 for x is equal to 0.3. Which is to say, we need some information. We need to remember the Maclaurin series for cosine of x up to second degree. So the second degree polynomial that we're using is 1 minus x squared over 2 factorial, technically. So we need that. We're centering it at 0 because it's a Maclaurin series, and we know that the point we care about is 0.3. So if I'm interested in cosine of 0.03, I know that the value itself is approximately 1 minus 0.3 squared over 2, thanks to using the polynomial itself. And we know from our theorem that the error would be less than or equal to the result that I'm working with, right, the point I care about, minus the center, to the power of n plus 1, so to the 2 plus 1 power, divided by n plus 1 factorial, by which I multiply the maximum of, I'm doing n equals 2, so I need 3 derivatives of my function cosine of x. And I'm just going to note evaluated at any x in the interval from 0 until 0.3. Big trick number 1, big idea, the thing you need to remember, the thing you need to be okay with. I'm not computing this at all. I don't care. When I take derivatives, I get sines and cosines, and the maximum of sines and cosines is 1. This max is less than or equal to 1. I'm not going to bother finding exactly what it is. I just don't care. Because this stuff is going to be small anyway. So what's the difference making it a little bit smaller? We're not finding the error. We're finding a bound for the error. We're saying the error is definitely not worse than this. So my approximation, my bound's going to be a little higher than it has to be. I could use a number for this max that's smaller than 1 so that my bound is smaller, but whatever. Close enough, right? We don't need perfection. We're just bounding things anyway. So I find that I know for sure my error is less than or equal to 0.3 cubed divided by 3 factorial times 1. It's in fact less than something where this is smaller than 1, but it's definitely less than when it's 1, right? The max is definitely less than 1. Which in turn becomes, if you literally compute this, we have that the actual error of using this approximation is less than or equal to 0.027 divided by 6, which comes out to be 0.0045, because 270 over 6 is 45 cents. So what do we know? We know that the true value of cosine of 0.3 is less than or equal to 1 minus 0.3 squared over 2 plus 0.0045, and it's greater than 1 minus 0.3 squared over 2 minus 0.0045. That's pretty good, right? Like, this is already small enough that I'm really not worried about it. This seems pretty good to me. Not bad. So that is bounding our error and then bounding the actual value, right? We know the true value lies somewhere between these two things. Not bad at all. Not bad at all. We're going to do a second example. Example 2 of a different type of problem. The problem this time is to find values of x such that the third degree Maclaurin polynomial for sine of x has error no greater than, that is an alarm that I have to go do something real quick. I'm going to pause, but you won't know the difference unless you look at the clock. No greater than 0.05. So other way around, right? We're already saying I want to make sure my error is less than this. I know what function I'm using. I know what degree polynomial I'm using. I want to find the x's that let it happen. So let's keep in mind, we know that our error is definitely less than a certain thing, and we want to make sure that we're less than 0.05. If my bound is less, my actual error is definitely less, right? The thing we can put in the middle is, well, I don't know what x I'm using, but I know that I would subtract it from the center and use my n plus 1, so 3 plus 1, and I would divide that by n plus 1 factorial, by which I multiply the maximum of the n plus first derivative of my function sine at all values that lie between my center and my x, right? I don't know what x is, but I'm allowed to consider any value of z that lies between 0 and that point. So once again, I'm just going to make life easier, right? I'm just going to say this, it's definitely less than 1, right? So what I know is, if I make this 1, my error is definitely small enough. So if I make my bound when the max is 1 less than something else, my error is definitely small enough, right? If all I knew was the statement, if all I knew is that the actual value with the true max was less than 0.05, I couldn't make this bigger, right? Because that might be too big past 0.05. So I really shouldn't have put this yet. That really muddies the water. We know our error is less than this. And we know that even if I make the max too big, my error is still less, right? So I know that my error is less than or equal to x to the 4 over 4 factorial times 1. And I want that thing to be less than 0.05, right? If this is less than 0.05, then my error is definitely less than 0.05. 4 factorial is 24. So I get that x to the 4 should be less than or equal to 0.05 times 24, which is 1.2. So that x should be less than or equal to 1.2 to the 1/4, right? 1.2 to the 1/4. And therefore, I have computed that. This tells us that x is less than or equal to 1.046 and change. Something is under the, oh. 1.046 and change. By symmetry, it's the same error on both sides, right? Whatever's happening on the left and on the right, the value of sine is just negated anyway, so it's the same idea. I can bound the error the same on both sides, is what I really should say, right? Because if my x were negative, I'm raising it to the 4 anyway, so it becomes positive. So my x can be on either side here. It's really plus or minus. Therefore, I have negative 1.046 is less than or equal to x is less than or equal to 1.046. So as long as I choose values of x between negative 1.046 and positive, that's a little more strict than the real value, which depended on an approximation a little more strict than the best possible bound. And my error is less than this bound anyway. So all over the place, we're making approximations, right? This isn't exact, and that's okay. Maybe numbers bigger than this would also give me an approximation of sine of x using a third degree polynomial where the error is less than or equal to 0.05. But I know for sure this will work. Maybe more works too, but this definitely will. Okay? And there's an example of this type of problem, as well as having done an example of find a bound for the error. And that concludes the examples that Kirk is going to add in for the video about Taylor polynomials and approximating values.